So limits is basically the introduction to what you're going to start when you get to calculus. Stuff with the limits already, you just haven't known it, basically. So when you were learning algebra, say if you took college algebra here, or pretty much most college algebra courses, you talk about end behavior of polynomials and asymptotes of rational functions, and those are limits essentially. The limit of a function, basically you're saying as x goes towards some number, it approaches something, what happens to y? So what value does the function itself approach? So when we're looking at end behavior, we're usually looking as x goes to infinity or negative infinity, what happens to y? Y usually goes to positive infinity or negative infinity. And when we're looking at asymptotes, we're usually looking at the horizontal asymptote when we're looking at the limit. But you can actually do limits as far as vertical asymptotes as well. So actually, before I move on, I need to point out that we have specific notation here, and you guys know that I'm a stickler for notation. It's really important for you to write down what you are intending to write down. So we use lim, and if you do decide to type your work, this actually is in Microsoft Word. Actually, let me open up Word so I can show you guys. I think about half the class types their work, half the class doesn't. So I'm going to just open up a Word document here. When you go to insert an equation, and this only works in the desktop version, right? Insert an equation. It's under this thing that says limit and log. And so we want the one that says lim. And then I'm going to zoom in here so you can actually see what I'm typing in. So when we have a limit, we're saying x goes towards some number. So the way you type it is you have x in the bottom, and then I hit a dash, and then I use the caret symbol, or I guess it's not a caret, it's the greater than or less than symbol. The greater than symbol, which is also on the period, and it will automatically turn that into an arrow. That's what it looks like if it doesn't convert it to an arrow. I type a dash, and then I type that greater than symbol, and then it turns it into an arrow. So I just undid that, it did that. So then you type in where you want to go. So if it's towards a number, you just type in the number, and if you want infinity, it's actually right up here, one of the first things. So you can just click infinity there. And then you can fill in your equation, whatever you're taking the limit of here. So if we're just taking some equation f of x or whatever, we can just type that there. And then the limits is you copy and paste as needed so that you don't have to retype this the whole time. So that's the notation. So you're having x, and then that arrow says that we're going towards something. We're either heading towards a specific number, or we're usually heading towards infinity or negative infinity. And then f of x, that's what we're taking the limit of. So the limit of f of x as x goes towards some number equals, and then it usually equals a number. The limit can equal infinity or negative infinity as well. So that's the notation. That's the notation you're going to want to use, especially when you go to calculus, because that's the notation you're going to see. So now I can go to my next slide. So let's talk about end behavior of polynomials, just as a reminder, and so you can see how the limits here work. So when we have polynomials and we're looking for end behavior, we use what was called the leading coefficient test. And so basically, when we're looking at this, we're looking at what happens when x goes to infinity or negative infinity, and we're just looking at what happens to those end parts of the polynomial. And it usually down for a polynomial. So if your degree of the polynomial is odd, such as a cubic, you'll see the two top graphs here. And the coefficient of that cubic, that's the highest coefficient, an. So if x is cubed, then it's just the coefficient of that cubed term. If that's 0, then we say that it falls to the left and rises to the right. So this is falling because it goes down, and then let's erase my line, and then it's rising to the right. And then if it's odd, but the coefficient is negative, it just takes the reflection. So now it rises to the left and then falls to the right. So we're kind of looking at what happens as we move to larger numbers or smaller numbers. So you're starting at the middle at 0, and then you're moving up or moving down. Then if your exponent, the degree is even, so if it's something like squared, then they're going to be heading the same direction. So if the coefficient of the squared term is positive, then both sides rise. And if the coefficient of the squared term is negative, then both sides fall. So this is just a kind of refresher of polynomials and the leading coefficient test. This is actually in the textbook. I don't remember, I think it was section 1.5 where they talk about this. It might not be, it might be in another section, chapter 1, but it is in the textbook, and I just, just doing a refresher of these. So to connect that to limits, here's how we would write that. So usually when you were in college algebra, you were describing, you would draw a picture, or you would say it falls to the left or rises to the right. When we talk about limits, now this gives us a notation to talk about it so that you don't have to describe it in words. Now you have notation. So if I start with one that's odd, so if it's odd and the coefficient is positive, then we would say the limit as x goes to negative infinity. So that's as we're going to the left side here, and I'm going towards the negative numbers. Except my graph itself gets more negative, so that's going towards negative infinity. And then the limit as x goes to positive infinity, so that means as my graph goes further to the right, my actual graph itself is going up towards positive infinity. So now this is giving a notation to indicate that whether it falls or rises. It falls if it goes to negative infinity, it rises if it goes to infinity. And then it's basically reversed when you have a negative coefficient. So that way, when x is going towards negative infinity, the graph is going up towards infinity. Or when x is going towards positive infinity, our graph is going down towards negative infinity. So this is how you could write end behavior with limit notation instead of trying to describe it in words, as we did in college algebra. So likewise, when you've got the even degree, if the whether your x is going to negative infinity or positive infinity, both limits are infinity. Basically, y is going towards infinity. It's just going to go up forever. And then you've got the opposite when it's a negative coefficient. The limit as x goes to negative infinity is negative infinity because it's going down. And then as x goes to positive infinity, our graph is going down, so that's also negative infinity. So do you guys have any questions on the notation here or how you read it or anything that I've covered so far?
No, I don't think so.
Okay. So next I'm going to make the connection to asymptotes. So again, I'm going to start with a refresher of rational functions. So the rational functions, that's where you have a fraction and then you have a variable in the denominator. And we have three types of asymptotes. We have the horizontal, the vertical, and then the oblique or the slant asymptote. So we had a vertical asymptote when your graph approaches infinity when x goes to some number. So that line x equals a number is a vertical asymptote. As you get close to that line, your graph is either going up or down. And the asymptote has an equation y equals some number. And so that's basically your graph will hit that number, get close to that number as x goes to infinity or negative infinity. And then when you've got an oblique or slanted asymptote, your graph approaches that equation when x goes to infinity or negative infinity. And I just found a typo. It should be a y. That's a terrible looking y. There we go. So looking at this graphically, I've drawn the basic shapes for rational functions here, just so you can see the horizontal and the vertical asymptotes. So these can be anywhere in the graph, but you can have four basic shapes where you've got Like for the vertical, they're going in opposite directions. Or you can have the vertical asymptote, they're going in the same direction. And then you can have the negative version where it's basically reflecting either one. So those are the four basic shapes of rational functions. And so let's connect that to limits itself, because this gets a little interesting. So I'm going to start with this, the first graph. So we have a horizontal asymptote at y equals b, and then we have a vertical asymptote at x equals a. So these are just some numbers, a, b, whatever the numbers are. So the limit, how we connect this to limit. And every time I try to hit the pointer, it doesn't actually let me zoom in, unfortunately. So if we're looking at the vertical asymptote, what happens is, as you're approaching this x value of a, from the right, it's going up to positive infinity. And then as you're approaching the value of a from the left side, it's going down to negative infinity. So we've got two different directions here, depending on what side you're getting to that vertical asymptote in. And we indicate this in our limit notation by using plus and minus. So when we're looking at this limit, I'm going to highlight this. You can see I have a plus and a minus. Plus and the minus are in the exponent, essentially. Those are telling you, are you coming from the positive side or the negative side? That's what that's saying. So a to the positive, this is coming from the right. So you're basically going right to left when you're looking at your vertical asymptote or your limit. And then when it says a negative, you're going left to right. You're going from the negative side heading towards the positive side. And so our limit is different because our graph is heading in two different directions. One side it's heading to positive infinity, the other side it's going in negative infinity. If we compare that to the second graph here where they're heading in the same direction, for the vertical asymptote, we don't have to do a plus or minus because they're going in the same direction. Whether you're going from the left or the right, both sides are heading up to positive infinity. So you can just write x goes to a. You don't have to indicate whether it's from the left side or the right side, because both sides are the same. Now the vertical asymptote. So now we're looking at what happens when x goes to infinity or negative infinity. Or I'm sorry, I said vertical, I meant horizontal asymptote. And so that's where your y value actually approaches a number. So when x goes to infinity, so as my graph is going far to the right, I'm going close to this line y equals b. So my limit is going to be b. That's where we're approaching. And we're approaching that same limit as x goes to negative infinity. We're still looking at that line y equals b. So the number that our graph is heading towards is b. And it looks the same on this side. So it doesn't matter what happens to, like, whether the vertical asymptote doesn't matter. The horizontal asymptote, as x goes to infinity, we approach b. And as x goes to negative infinity, we approach b. And that's going to be the same. It's just a new way of kind of writing the notation here. Are there any questions on these two pictures here, or what I've done here?
I just want to make sure I'm understanding this right. So on the right example, the vertical, I'm not going to try to say that word.
Yeah, asymptote.
Asymptote? Yeah.
Yes, it's like a silent P.
So the limit of f of x is infinity. So as y goes to an infinity number, x continues to a positive number.
We're saying when the limit is infinity, what we're saying, and I'm gonna, as my x value, as I'm heading towards my vertical asymptote, whatever this number is. Yellow was a very poor choice. Do that in it. So as my x is heading towards that value of a, I'm saying what happens to y? Well, y is heading up towards infinity from both ends. So the answer for the limit is basically what happens to y. And then the underneath the limit part is telling you where are you looking at? What are you doing with your x? Does that help?
So in other
So
words,
like,
that bottom part is moving towards A,
Yeah,
and
so that
that's
bottom
defined with
part,
the arrow.
yeah. So that bottom part, that's as x goes towards a. And then we're looking in both directions. And then what is happening to y? And that's what we put after the equal sign.
That makes a little more sense if you look at it from the x value first. So on
Yes.
the horizontal on that one, as x goes to infinity.
Yes. So if I erase these, so as x goes to infinity, that means as x is going all the way out there, what is happening to my y value? Well, it's heading towards b.
Yeah. 0, yeah. We don't leave the graph.
Yeah, and then on the other side, if we're, as x goes to negative infinity as I'm going here, what is happening? Well, my graph is also heading towards this horizontal asymptote of b.
Okay. I got it.
But I can also draw this on here because I've got the two other pictures here. So like if we look on the left, if we're looking for the vertical asymptote, and we've got this a plus and a minus. So the a plus says as x is going towards a from the positive. So I'm only looking at the right side here. So as x is heading towards a, which is that vertical asymptote, what is happening to y? And y is heading down towards negative infinity. So that's why this limit, this first limit, as x goes to a from the positive side or the right side, right to left, goes down to negative infinity. The one underneath it, when it says x goes to a to the negative, so that means we're going from left to right. So we're starting at the negative side, and now we're heading right until we hit a, basically. And then we're saying, okay, as we do that, what's happening to x? Well, not x, what is happening to y? Y is going up and up and up towards positive infinity. So the limit there is positive infinity. If we compare that to the one on the right, when it says x goes to a, that means we're looking in both directions. So as we're heading to a from either side, our y value on the graph is going all the way down to negative infinity. That's where the graph is approaching. So our limit as x goes to a is negative infinity. And then for both of these, the horizontal asymptote limit is exactly the same as the other ones. So does this add some additional clarification with these two pictures?
Yes, that makes more sense now.
Okay. Are there any other questions on this?
I don't think so.
Okay. So now that we've sort of connected that to things that you've seen already, next is to actually find limits. So there are basically three ways to do this. We have the numerical approach, where you basically make a table of values. You have the graphical approach, where you look at the graph and then you figure out what happens. And then we have the analytic approach, where you're basically using algebra or calculus. So obviously, you're not learning calculus in this class, so we're only going to be doing it versus using some algebra. And because of that, we can only do the rational functions and the end behavior ones, because that's the only type of limit that you know that you've done with algebra. There are other different types of limits, but they require calculus techniques. So we're not going to do those with the analytic approach. The more complicated ones that are not polynomials or rational functions, you have to use either the numerical approach or the graphical approach. And I actually recommend doing both of them because the numerical approach can be a little misleading without a graph to help you interpret it. So I'm going to start the same order that basically we have sort of things on the assignment for this week. I'm going to start with the numerical approach where you're making a table of values. So it says estimate the limit using a table of values. And so I have this limit as x goes to 0. And then what is after that is my function. I'm not going to use the green here. So we're looking at some function f of x, which is e to the x over x squared minus 4. And so we're looking at what happens as x goes to 0, because that comes from underneath here. It says arrow 0. So that's why I put 0 in the middle of my table. So when you're looking at the limit, you're looking from the left side and the right side. It's just like in my pictures here. The next one here, when you're looking for that limit at a specific number, you're looking at the left and the right side of it. So we're going to do the same thing when we make this table. We need to pick numbers to the left and to the right. And you start with that middle. You're starting with the number that it's telling you you want the limit at, and then you have to go from there. The general rule is that you want numbers that are close to there and then work farther apart. And you want to start with the really close. So the best numbers to pick is 0, 0, 1 as the next one to the right of 0, and then remove a 0 each time. And then you want to do the same thing in the negative direction. So this would be the general guideline that I would use if you're ever asked to make a table and to find a limit. You start with your center, and then you move to the right and to the left and kind of make sure you're doing a positive and negative version. You're going to start small and then remove like a decimal place each time to get slightly larger. But we want it to be near 0 because we're looking at what happens as we go close to 0. And I think this is the same table that's in that first problem on the assignment. So when you're doing a table of values, you are basically plugging each of these numbers into f of x. So this is very calculator handy, or calculator intensive. So my first table value of negative 0.1. So I need to plug negative 0.1 into this equation. And then you have to basically plug and chug this into your calculator. It's time intensive, so I'm going to actually show you some way that you can save time. And you can do this by opening up Desmos. So I've put the equation in Desmos already, and I'm actually, well, if you go to this plus sign, you can add a table. So I'm going to move this, table after f of x. So my x values, I'm going to put in these x values from, it got too close. I want to be able to see what I'm entering in. I'm going to put in my x values from the table. So I'm going to put in negative 0.1, negative 0.01, negative 0.001, 0, 0.001, 0.01, 0.1. So I'm filling in my table with my x values. Now here's where the fun trick comes in. I have put in f of x for the equation that we had. E to the x over x squared minus 4. This second part where it says y sub 1, delete that, type in f x, and then you put the underscore 1 to tell you to use your table values. And then it fills in all the numbers for you. And so that way, instead of just putting this in your calculator and having to calculate all this stuff by hand, you can make this table and then it will do it all at once for you, and all you have to do is copy it down. Now, generally we round either 3 or 4 decimal places. I'm going to round to 3 decimal places, and so I'm going to take these numbers and then write them in. So let's see, we've got negative.
How did you get the underscore 1 on there?
Good question. That is an excellent question. So, you know where the minus, yeah, there's a shortcut key. So where the minus is on your keyboard, if you hit shift and then the minus, that puts you as an underscore.
Okay.
Yeah, nice little trick. There's not, let's see, I don't think there's a, yeah, I don't see a shortcut to do it. Oh, here's another option. If you don't do that, if you expand your keyboard, it defaults to the 1, 2, 3, but if you click A, B, C, then it has this A and then a sub B button. You can use that to get the same thing. All the way at the bottom here.
My popcorn was blocking that. I couldn't see that on my computer screen.
Yeah, it's all the way at the bottom. Let's see if I can, there, it's right there. Put it in the middle. It's this A, B. So I've got this
There
A,
we
B,
go,
C. I
yeah.
click that. There you go. That will also get it to you. So I had these written down on a separate sheet of paper so that I didn't have to go back and forth copying from my table. So I'm going to pull that out and then just fill in my table here. And I already rounded these to 2 decimal places. So I'm going to just fill these in for you. So I filled in the table, and then the question is we're estimating the limit. So we're saying, okay, as x is heading towards 0 in either direction, what is happening in the y value? What number is my y value approaching? Where is y heading? And our y value is actually the same for 3 of these. So it seems pretty clear that as you're going to from the left to right and right to left as you go towards 0, your y value is looking at negative 0.25. So the numbers on either side of that are getting closer to 0.25, and then they're getting further away as you, like if you go from left to right, you're getting to negative 0.25, and then it goes away. But that number in the middle where it's going towards, that is negative 0.25. So that is our limit. So we would say the limit as x is heading towards 0 from either direction of e to the x over x squared minus 4 is equal to negative 0.250. Since that's what our numbers are looking like, where they're heading. Does that make sense?
Yes.
Okay, and it's all about picking the right numbers. So that's why you want to start with your middle number, the number you want to approach, and then you go from there. So to make it easy for us, I'm using the same function. I'm just now approaching a different number. So now we're saying, okay, we're approaching negative 2. So instead of x going towards 0, it's x going towards negative 2. So now negative 2 is my middle number here. So what do we do? How do we, determine where our left and right? So I'm going to use the same basic numbers that I had before. I'm going to just write these above, and then I had 0, and then 0.001, 0.01, 0.1. So in order to kind of determine what numbers I'm going to use in this table, with now that I have negative 2 as my center point, I'm going to subtract 2 from each of my original numbers. So going from left to right, if I have negative 0.1 and I subtract 2, I'm now going to have negative 2.1. And then this will be negative 2.01, negative 2.001. So I went from 0 to negative 2, which is subtracting 2. So I'm subtracting 2 from all of these numbers to kind of reset where my center is. I'm just shifting it over so that it's centering the right number. So then when I have 0.001 minus 2, this gives me negative 1.999. And then I get negative 1.99 and negative 1.9. So I'm just shifting my original table over to, so that I still have the same distribution. I'm still looking close to my number. It's just now it's centered somewhere else. Does that make sense?
Yes.
Okay, so if it said if your x going to 5, you would add 5 to each number, and then that would make sure everything is centered at 5. So then we just change our table. So going back to Desmos here, and I don't think it's gonna, I'm gonna have to just change all of these numbers. 2.1, 2.01, whoops, 2, that's now -2, -1.999, 1.99, -1.9. So I can just shift those numbers. And now I've got different numbers here, and actually we have undefined as one of them because that means we're dividing by 0, which we can't do. So I've shifted over my table, and now I'm going to plug in sort of those numbers here. So I'm going to go back, and again, I rounded these for us already. So we get 0.299, 3.341, 3.792. This is undefined. -33.876, -3.426, -0.384. So those are the numbers that I got from the table, and now we have to determine what happens. So again, we're looking at what happens when x is going towards -2. So when x is going towards -2, our y values seem to be increasing dramatically. So they're going from like close to 0, and then they're getting higher because it's like 0.3 to 3 to 30, you know, like they're going up much higher. And then when we're looking at from the right side as we're heading towards -2, now our y values are negative, but they're getting more negative. They're kind of going in this opposite direction here. And then we have that point where we're undefined in between. So if you're looking at the y values, we're going in two opposite directions here. So when we're finding the limit from a table of values, we say, is there a number that I am approaching this? And we're looking for the same number that we're approaching from both sides, because we're looking at from both sides, because it just says x goes to -2. It's not indicating from the left or the right side. So we're saying, as we go to -2, is there a single value that y is approaching?
Yeah, no.
That's
No,
correct.
because it's going toward positive.
Exactly. It's going towards positive and negative infinity. Both sides, they're not matching up. And so when we have a case like this, we say that our limit does not exist. And I don't know if anybody has ever seen Mean Girls, but that is near the end of the movie. That's a famous quote, that the limit does not exist. So we usually abbreviate it D and E. Because in order to have a limit without specifying from the left or right, it has to match. So if it doesn't match, we say that the limit does not exist, because they're going in two different directions. And it's usually hard to determine that from a table, because if you look at the numbers on the table, you might be inclined to say it's going towards 0 because it's 33 on one side and -33 on the other. That's why kind of drawing this picture like I did of the y values helps you see that it's not actually going towards 0, because they're kind of heading in two different directions. So when I was saying that there's three different approaches, the numerical approach is not always the best approach, and I like to do it with a graphical approach. And so going back to Desmos, I'm going to actually turn on what the graph of this function looks like. So it looks really interesting. And I'm going to put in, first we're looking at what happens when x goes to 0. So I'm going to just type in x equals 0, and I want to change the color. And so our limit when x went to 0 was an actual number. So if I zoom in, we got -0.25. So you can zoom in and you can see actually the limit is -0.25. When you go towards 0 from the left, you're nearing that number, and then you're going from the right to the left. So from left to right and right to left, you're still approaching a y value of -0.25 at 0. So that was that first example we did, and we used the table. We found the limit was negative 0.25, which is the exact value at that point. The other one, the one we just did, is negative 2. So zoom out a little bit. We're at negative 2. So there is no value, and you can see that it goes in opposite directions there. And so you can look at the graph and say, okay, we're not approaching the same thing because one side's going positive, one side's going negative. And so that's where we say the limit does not exist, because they're not meeting. They're going in two different directions. And so looking at it graphically really helps you see that. Does that make sense? I hear that noise.
It's really making me look forward to calculus next term.
You know, the limits is the hardest part of calculus to understand. The actual calculus that you do is actually not so bad because it's basically algebra with new techniques. We're going to do more graphing once, don't worry. I'm going to just put in the picture for that graph here. Okay. Here's a different one. We're going to use a graph only. We're not going to do the table for this one. We're going to estimate the limit. And we're looking at what happens when x goes to 4, and then we have x plus 5 over, and then x minus 4 quantity squared. So this is a rational function. This is something that we could find the actual limit for algebraically, but we're going to do it with graphing. So I have already entered in that graph and what it looks like. So I'm going to just zoom out. So this is what the graph looks like that we're given for example 4. And then we're saying what happens when x approaches 4. So I'm going to put that on the graph and just as a dashed line so I can see what happens when I'm going towards there. So when x is approaching 4, which is my dashed line here, if I'm going from left to right, I'm going up and up towards positive infinity. And then if I'm looking at my graph from right to left, as I head towards 4, I'm also going up to positive infinity. So both sides are heading up towards positive infinity as we get closer, and you can even zoom out and you can see how it gets closer and closer, and you know it's going to keep going up towards infinity, get really large numbers. So that means our limit here is infinity based off of our graph. So when it says to use a graph to estimate the limit, you can put a little vertical line at where you're looking for. It says x goes to 4, so you can put a vertical line there so you can make sure you're looking at the left and the right side here. And then you're saying what happens to y when I'm looking from both directions. And y is going up towards infinity. So is infinity. And I can even do a little sketch here. So we've got basically a vertical asymptote here at 4. Is looking like this. It's a really terrible sketch, but basically you can see that sketch, and so we're going up towards infinity as we head towards 4 from either direction. Looking at, oops, not black. From the left here, and then from the right here. I mean, from the right and from the left. I got my left and right mixed up there. So are there any questions? Does that kind of clarify things a little bit?
I think I'm getting it, but I guess we'll see when it comes my turn.
I'm trying to pick ones that are also like, we're going to get into ones that are similar to the homework. Actually, most people do really well on the homework, so I think you'll find that it's not so bad. Okay, now here's another one. This time we have a piecewise function. And so it says use the graph to estimate the limit, and it's saying the limit is x goes to 0. So I'm looking at what happens as I head towards 0 in both directions. And so if we're looking for both directions here, as x goes to 0, and if I want to say if I'm going from left to right, I'm going to put that little negative sign sort of as an exponent there. So as we're going towards 0 from left to right, and we're heading towards the origin, where is y going? What y value are we heading up towards?
Towards infinity.
Stop at the center, though. Stop at where...
Well, it's 2 in one direction and 0 at the other?
Yes, yeah. So as we're going towards it, we're going to stop at the center where x is 0. So we're basically going up to 2 here. So the limit as x goes to 0 from the negative side is 2.
Mm-hmm.
And then as x goes to 0 and we're going from right to left, or going in the other direction, it's actually oops, I wrote f of x. It's actually heading towards 0, because as we're going from this right to left, my graph itself is going down towards 0 and then stopping. So I have two different numbers here. On one side it approaches 2, the other side it approaches 0. So since these don't match, we say the limit as x goes to 0 without the plus or minus symbol, which means both sides. This is another one where it does not exist because they don't match up from both sides. So there's basically a gap at this point of 0 that we're looking at. One side goes up here, the other side goes down here, and they don't match. Are there any questions?
So if they come together, then we would have had an answer.
Yes. Yeah, if they came to the same point on either side, you would have had an answer, and it just depends on, we would have had to draw the graph differently. But yes, if they match on both sides and they head towards the same number, you have an answer.
But if you see a graph like this, you should pretty well automatically know that you're likely going to have a DNE.
Yes, but it depends on where you're asking for. So like I looked at if we're saying as x goes to 0. But if it said as x goes to, say, like -2 right here, it goes to the same direction on both sides. So it depends on where it's asking you to look at. So if it said as x goes to -2, our answer would be 0 because our graph heads towards 0 there. So you have to really pay attention to what number, where it says x is going. Any other questions?
Not yet.
Here's another one. And there's one similar to this on the assignment. So again, we're given something that's sort of piecewise, but instead of two parts that don't match, we have just a hole in the graph, and then we have that point somewhere else. And so we're saying, what is the limit as x goes to 5? So we're looking at what happens, oops, not the highlighter, as x goes to 5 from the right and from the left. So as x is going from the left, my graph is going all the way up, and it's approaching our hole, basically. So if I was to write this, my limit as x heads towards 5 from the left, so we're going from left to right, from the negative side of f of x, it's going up to 5. There's a hole there, but that's where the graph is heading. Then I look from the other direction. So as I'm heading towards 5 from the positive, my graph is heading down here, it's also heading towards that hole. So we would say the limit as x goes to 5 from the positive side, so going from right to left of our function, that is also approaching 5. So that's where the graph is heading. Even though we don't have a number there, that's okay. So this tells us that the limit itself, because it matches on both sides, is equal to 5. Even though the actual number at x equals 5 is not 5, that doesn't matter, because we're not asking what is the actual value at that location. We're saying where is the graph heading. So the graph could be heading to a completely different number than what is actually there. Do you see how that was working there?
Yeah, I can see what's going on in this one.
Yeah, I think for a lot of these, drawing a picture is the best way to do it. And then draw your arrows. Where is my x going? And then follow your graph to see where it's going. It's, you know, it's like you're filling in the blanks, filling in the, like what is happening if I kept going in this direction? What is the pattern? Where is it going? Are there other questions or any questions?
So in the actual function equation there, with the x cannot equal 5, that's why it's the open circle
Yes.
at that position,
Mm-hmm.
solid circle at the 3 position.
Yeah, because it's saying 1x is equal to 5, it's 3. So that's not our limit because that's not where the rest of the graph is going. So when you're doing these, basically get the graph and then ignore the equation and just see what is the graph doing.
Right, that's kind of what I was thinking. You know,
Yes,
more of those
yeah.
equations.
Mm-hmm. It's all about the graph. Okay, so now I've got 2 that I'm going to do algebraically, because these are the only 2 types that we can. If we have a polynomial, and then if we have a rational function. And so find the limit algebraically, or they'll say like analytically. So we've got a polynomial here. And when it says that x is going towards infinity, this is telling us that we are looking at end behavior. Because we're looking at what happens as an x gets really big. So to do this algebraically or analytically, this is where we're looking at our leading coefficient test that I talked about at the very beginning. And so first we have to determine our degree of the polynomial, and we're going to write that down. So our degree is the highest exponent, which is 4. Which means that it's an even, so they're going to go in the same direction, the end behavior. It's going to be up or it's going to be down. Then we look at our leading coefficient. And that is the number in front of that x to the 4th term, so that is 3. So that's positive. So those 2 things are telling us it's going to look like a parabola where we're opening up. So when you're doing this algebraically, you're writing down like, okay, this is the directions, this is the test we're doing, here's the degree, here's the leading coefficient, here's what the picture looks like. So you're not like, it's not like you're solving anything, you're just using algebraic techniques, things that we learned in algebra.
Okay, considering that I learned my algebra 20 years ago and I'm having to put it all back together slowly.
Yeah, so it's not going to be as fresh.
No, it's definitely not as fresh.
Yeah, so that leading coefficient, that is just that number in front of that x to the 4th term. So you look for the highest exponent and then the coefficient for that. Yeah.
And how do we know because of that leading coefficient of 3 that it's going to be a parabola going up?
that, and this is, let's see, let me find the right slide here. So our degree, the exponent is even, and then that coefficient is, that's why I gave these, so that way you guys can download this, and then you don't have to try to remember you actually have this, because then it also tells you what the limits are. So in our case, we're looking for when we're going up to infinity, so our limit is going to be infinity.
Okay, all right, that makes more sense now.
Yeah. So going back. So once you've determined all of that, we're looking at as x goes to infinity, so we're looking at this right side, which is going up to infinity. So we would say, we would write the limit as x goes to infinity of 3x to the fourth plus 5 is equal to infinity. Are there other questions?
No.
Okay.
So basically, you're taking your, you take the largest degree number
Mm-hmm.
in that equation. So if it had been a 5, it would have been odd. So
Yep.
odd, the leading coefficient would have been greater than 0. It would have been the inverse of this parabola, correct?
Yes,
correct?
roughly.
I didn't get to write all that down initially.
Well, yeah, tomorrow I'll be sharing this with the PowerPoint, so you can download the PowerPoint so that you have it. Yeah, if it's odd, we're looking at the one on the left here. So the actual, if it was fifth odd, the answer would be the same, but the picture would look different.
All right. Okay.
Okay, now the last one that I have here is the rational equation. So this is 5x plus 2, and then x to the negative 4. And it is saying that we want to find the limit as x goes to negative infinity. So if it's saying when x goes to infinity or negative infinity and you have a rational equation, that is telling you you're looking for a horizontal asymptote. So we have here a rational function because we have a fraction. And this is telling us we're looking for the horizontal asymptote. So in algebra, when we teach how to find the horizontal asymptote, we say that you look at just the highest terms. And then if the top is smaller than the bottom, it's always going to be at 0 if you're looking at the degree. So if it was like an x squared on the bottom and x on the top, it's always y equals 0. If they have the same degree, here we have an x on the top and an x on the bottom, then we look at the coefficients. And then if the top is larger than the bottom, you have to do long division. So I'm going to show you how to do this using limit notation because this is what you'll do when you get into calculus. So what happens is, I'm going to first rewrite what we have. Whoops. Make sure my negative doesn't disappear. X goes to negative infinity. We have 5x plus 2 over x minus 4. So if you think about what happens, as x is getting really, really small and it's going to negative infinity, you're doing 5 times negative infinity plus 2. Plus adding 2 to something that's close to negative infinity doesn't really matter because you're basically still going to be near negative infinity. And in the bottom, you have x minus 4. Well, if you're basically going to negative infinity and then you're subtracting 4, you're still at negative infinity. So when we're taking the limit, those numbers that are added on don't really matter. And so we can just ignore them. And so this is the same thing as taking the limit of 5x over x. Because adding 2 to infinity or subtracting 4 from infinity doesn't really do anything. So now we can ignore those, and now we just have something with that we can just cancel because we've got an x and an x. So those basically just cancel out. And so what we really have, and it's really important, you have to write the limit part every time here, is when those cancel, you're just looking at, okay, we have 5. As x goes to infinity, or x goes to negative infinity, what happens to 5? Well, 5 is still 5. Like, it's not going to change. It's always going to be at 5. So our answer here is 5. So the part that you're taught in algebra is basically you're taught to write it something like this. And then basically you see that the x's cancel out and your answer is 5. The part that is the calculus approach is everything that I wrote here, is all these extra steps. Is kind of explaining, well, why are we allowed to do that? So, you know, adding a little bit of numbers to something really big or really small doesn't really do anything. Then you can cancel out your x's. And then 5 is just going to stay 5 no matter what happens to x, because x is not involved at all. And so that's how we end up with a. And you can always check your work by graphing this. But this would be, if it asked you to do it algebraically, these would be the steps that you would show. And you have to write that limit part every step until you get your final answer. Are there any questions?
No.
Okay, so that was my very last example that I had for you guys. So don't worry if it's sort of confusing now, because you're going to see this again when you guys get to calculus. Like, this is going to be the first thing that you're going to see. But the homework, when you see it on the homework, I think it will start making sense. And because my limit video that's in the classroom already uses different examples, go ahead and watch that one as well, because it uses different examples but sort of the same techniques. So that can give you some more additional examples if you watch that. I'm not going to replace it. I'm going to just add this one as limits version 2, basically. So yeah, anything else that you guys have for me?
Are you going to be the Calculus 1 teacher for the next term?
Probably not. If you're lucky, you'll get Kay McGee, who teaches a lot like I do. She doesn't do the videos, but she's very good. So I hope that you get her, because they usually have me just doing the lower level math classes. But I don't know. I'd love to teach Calc 1 if they give it to me, but it's very unlikely. They haven't given it to me yet. So they usually stick me with the algebra and the pre-calc.
Okay. Yeah, this is my first semester, so I'm still getting used to the first week or two. Seems to get to the next instructor's techniques and methods, and the first couple of weeks usually has me all thrown off.
Yeah,
so
it's
this has definitely been a learning curve this first semester.
Yes, and you're starting with, starting your first semester taking a math class is pretty brave. It's harder when you're taking classes and they're only 8 weeks. You don't have a lot of time to get used to the instructor. Like if you're, on campus, usually those are 16 weeks. So you have time to get used to instructor. But if you have Kay, she's very similar. She does resubmission. She's very nice, gives really good feedback. So that will at least make the transition easier.
Good to know.
Yep. Other questions or comments?
I think I'm good.
All right. Yeah, so just as housekeeping, Tuesday's the last day for you guys to submit anything. So if you are going to do any resubmissions or anything, that's when you want to make sure they're in by then. I did start grading some of the assignments for this week, and they do seem to be better than last week, where everybody was all messed up on the units. So that's a good sign. And units are very, very important when you start taking like electrical engineering courses. I know some people here don't have to take those courses, but those that do, the units are very important. So that's why I was making a big deal about that. So
yeah, I'll have to ending up where I'm going to be heading. So
yes, especially because you have to, or if you have to take physics, because I think you guys have to, if you're in electrical engineering, I think you're required to take a physics class. But units are really important there, and with physics, they love to throw you off and give you the wrong units, and you have to convert it to the correct units before you can do the math. So I'm just trying to prepare you guys for those other courses, basically. Make sure that you're not thrown out of loop and be like, so that's why I was like, yeah, I'm harping on the units, but you guys can resubmit your work so you can fix all that. And so, yeah.
That'll be another one I get to jump right into physics 2, and I'm like, oh Lord.
Physics 2 is much more fun than Physics 1, in my personal opinion. Because Physics 2 is all the stuff with like electricity and magnetism. Physics 1 is all the stuff with like acceleration and momentum, and that I always had a hard time with. But when I got to Physics 2, I was like, this is easy. So.
All right.
All right. Well, if you guys don't have anything else, of course, you guys can reach out to me if you do think of things later on. But I'm going to make sure that I'm going to post this video and the PowerPoint tomorrow morning. And yeah, and that's it. That's what I've got for you guys. So.
All right. Thank you.
You are welcome. I will talk to you in the discussions or something, you know.
Yeah.
All right. Bye.
Bye.